Welcome to this lecture on integrated carbon capture, utilization and storage, or CCUS, and underground hydrogen storage, or UHS. In this video, we will explore how the subsurface can become a strategic platform for the future clean energy system. Traditionally, underground formations have been used for oil, gas, water, and geothermal resources. However, in the energy transition, the subsurface can play a much broader role. It can store captured carbon dioxide to reduce emissions, and it can also store hydrogen to balance renewable energy supply and demand. The main message of this presentation is that CCUS and UHS should not be considered as isolated technologies. They both depend on geological storage, reservoir behavior, pressure management, geomechanics, monitoring, and long-term risk control. By integrating them into a single dynamic simulation and digital twin framework, we can design safer, more efficient, and more valuable subsurface energy systems. In this lecture, I will guide you through the full concept, from CO2 capture and storage to hydrogen injection and withdrawal, then to pressure control, fault stability, monitoring, and digital twin optimization. The world is moving toward carbon neutrality, but reaching this goal requires more than simply installing more renewable energy. Renewable energy sources such as solar and wind are essential, but they are intermittent. Sometimes they produce more electricity than we need, and sometimes they cannot fully meet demand. At the same time, many industrial sectors, such as cement, steel, chemicals, and power generation, still release large amounts of carbon dioxide. This creates two major challenges. First, we need to reduce CO2 emissions from hard-to-abate industries. Second, we need long-duration energy storage to support a reliable energy system. This is where CCUS and underground hydrogen storage become highly important. CCUS allows us to capture CO2 and store it permanently underground. Underground hydrogen storage allows us to store clean energy in the form of hydrogen and use it when demand increases. When these two systems are integrated, they can support both decarbonization and energy security. This makes integrated CCUS and UHS one of the most exciting research and engineering directions for the future energy transition. Before going into the technical details, let me briefly introduce the roadmap of this video. The goal is to make the topic understandable step by step. First, we will look at the overall concept of an integrated CCUS and underground hydrogen storage system. We will discuss why combining these two technologies can create additional value compared with developing them separately. Then, we will move into the CO2 storage workflow. This includes CO2 capture, compression, transport, injection, plume migration, pressure buildup, and long-term trapping mechanisms. After that, we will discuss underground hydrogen storage, including hydrogen production from renewable energy, compression, injection, storage, and seasonal withdrawal. In the second half of the video, we will focus on dynamic simulation. We will discuss pressure management, brine extraction, geomechanics, fault stability, and monitoring systems. Finally, we will introduce the digital twin concept, where simulation, monitoring, forecasting, and optimization are connected in real time. By the end of this video, you should understand not only how CCUS and UHS work, but also why dynamic simulation is essential for designing safe and intelligent subsurface energy systems. What is an integrated CCUS plus UHS system? An integrated CCUS and underground hydrogen storage system is a subsurface energy system where carbon dioxide storage and hydrogen storage are planned, modeled, monitored, and optimized together. In a conventional approach, CO2 storage projects and hydrogen storage projects may be developed separately. However, both systems require similar types of subsurface knowledge. They need geological characterization, reservoir simulation, well design, pressure monitoring, caprock integrity assessment, and risk management. In the integrated concept, CO2 captured from industrial sources is injected into secure geological formations such as deep saline aquifers or depleted reservoirs. At the same time, hydrogen produced from low-carbon or renewable energy can be compressed and stored underground, then withdrawn when energy demand increases. The advantage of integration is that the same subsurface platform can be used more intelligently. Shared monitoring systems, shared data infrastructure, shared geomechanical analysis, and shared operational control can reduce cost and improve safety. Most importantly, Integration allows us to manage the subsurface as a dynamic system rather than as independent storage compartments. The CCUS process begins before CO2 enters the subsurface. First, carbon dioxide must be captured from industrial sources. These sources may include power plants, cement factories, steel production, hydrogen production facilities, or chemical plants. Depending on the source, CO2 can be captured from flue gas, process gas, or other emission streams. After capture, the CO2 must be treated and compressed. Compression is necessary because CO2 must be transported efficiently and injected into deep geological formations under high pressure. At suitable depth and pressure conditions, CO2 may exist in a dense or supercritical state, which allows larger volumes to be stored underground. The compressed CO2 is then transported through pipelines or other transportation systems to the storage site. At the storage site, injection wells deliver the CO2 into the target reservoir. Therefore, CO2 geological storage is not just a reservoir problem. It is a complete chain that includes capture, conditioning, transport, injection, storage, monitoring, and long-term verification. For dynamic simulation, we must consider the injection rate, pressure constraints, reservoir properties, and storage capacity from the very beginning. Once CO2 is injected into the reservoir, it begins to migrate through the porous rock. This movement creates what we call a CO2 plume. The plume shape depends on many factors, including permeability, porosity, reservoir dip, injection rate, pressure conditions, capillary pressure, relative permeability, and geological heterogeneity. In many cases, CO2 is less dense than brine, so buoyancy can drive upward migration until the plume reaches an impermeable caprock or sealing layer. At the same time, pressure gradients created by injection push the CO2 laterally away from the injection well. Therefore, plume migration is controlled by both pressure-driven flow and buoyancy-driven flow. Dynamic simulation is essential because plume migration changes over time. In the early stage, the plume may expand quickly near the injection well. Later, migration may slow down as injection stops, pressure dissipates, and trapping mechanisms become more important. For safe CO2 storage, we must predict where the plume goes, how fast it moves, whether it remains below the caprock, and whether it approaches faults or abandoned wells. These questions cannot be answered by static geological interpretation alone. They require time-dependent simulation. A very important point in CO2 storage is that the pressure front may extend much farther than the visible CO2 plume. The CO2 saturation plume shows where CO2 is physically present, but the pressure disturbance can travel through the brine-filled reservoir over a much larger distance. This is critical for safety because pressure changes can affect caprock integrity, fault stability, injectivity, and neighboring subsurface resources. Even if the CO2 plume does not reach a fault, the pressure front may still influence that fault. Therefore, risk assessment must consider both saturation changes and pressure changes. Pressure buildup depends on injection rate, reservoir permeability, reservoir thickness, boundary conditions, brine compressibility, and the presence or absence of pressure relief mechanisms. In a closed or low permeability system, pressure can build up rapidly. In an open system, pressure may dissipate more easily. This is why pressure management becomes one of the most important topics in integrated CCUS and UHS. Safe storage is not only about where the CO2 plume moves. It is also about how pressure changes across the subsurface and how those pressure changes influence geomechanical stability. Long-term CO2 storage becomes secure through several trapping mechanisms. The first is structural or stratigraphic trapping, where CO2 is physically contained beneath an impermeable caprock or geological barrier. This is usually the primary trapping mechanism during the early stage of storage. The second is residual trapping. As the CO2 plume migrates and brine re-enters the pore space, some CO2 becomes disconnected and immobilized as small bubbles or ganglia. This reduces the mobility of CO2 and increases storage security. The third is solubility trapping. Over time, some CO2 dissolves into formation brine. Dissolved CO2 is less buoyant than free-phase CO2, so it is less likely to migrate upward. The fourth is mineral trapping, where dissolved CO2 reacts with minerals in the rock and may eventually form stable carbonate minerals. Geochemical indicators, such as pH, can also help us understand CO2 behavior. When CO2 dissolves into brine, it forms carbonic acid and lowers pH. Therefore, pH maps from reservoir or geochemical simulation can provide useful information about CO2 dissolution zones and possible leakage signals. By combining saturation maps, pressure maps, pH maps, and geomechanical indicators, we can build a stronger monitoring and risk assessment framework. Now let us move to underground hydrogen storage. Hydrogen can be produced in different ways, but in the context of clean energy, a major pathway is water electrolysis powered by renewable electricity. When solar or wind power produces more electricity than the grid needs, that surplus electricity can be converted into hydrogen. After production, hydrogen must be compressed before storage. Compression increases the energy density and allows hydrogen to be injected into underground formations or salt caverns. The surface system may include electrolyzers, compressors, pipelines, storage tanks, and injection wells. Once compressed, hydrogen is injected into the subsurface. The target storage formation could be a salt cavern, a depleted gas reservoir, or a saline aquifer, depending on local geology and project objectives. Each storage type has different advantages and challenges. Hydrogen is much lighter and more mobile than CO2, and it also has different physical and chemical behavior. Therefore, underground hydrogen storage requires careful simulation of gas flow, pressure cycling, cushion gas, working gas, mixing, microbial activity, and containment integrity. The key concept is simple. We use clean electricity to produce hydrogen when energy is abundant, store it underground, and recover it later when energy is needed. Underground hydrogen storage is especially attractive because it can support seasonal energy storage. Batteries are very useful for short-term storage, such as hourly or daily balancing. However, for seasonal storage, we need technologies that can store large amounts of energy for weeks or months. This is where hydrogen becomes very powerful. During spring and summer, renewable energy production may exceed demand. Instead of wasting that energy, we can convert it into hydrogen and inject it underground. During autumn and winter, when energy demand increases, especially for heating and industrial use, hydrogen can be withdrawn from the storage formation. This injection withdrawal cycle can be repeated many times. The reservoir pressure rises during injection and decreases during withdrawal. Over multiple cycles, the system must maintain deliverability, gas quality, and mechanical stability. Dynamic simulation is essential because underground hydrogen storage is not a one-time injection process. It is a cyclic operation. We need to understand how the plume changes, how pressure evolves, how much working gas can be recovered, and how the system behaves over many seasonal cycles. In underground hydrogen storage, it is important to distinguish between cushion gas and working gas. Cushion gas is the volume of gas that remains in the reservoir to maintain pressure and support deliverability. Working gas is the portion that can be repeatedly injected and withdrawn during operation. This distinction is very important for project economics and energy planning. A storage site may have a large total gas capacity, but only part of that gas may be practically available for withdrawal. If too much gas is withdrawn, reservoir pressure may decline too much, reducing deliverability. If too little gas is withdrawn, the storage system may not provide enough economic value. The amount of cushion gas depends on reservoir depth, permeability, porosity, pressure limits, well design, and operational strategy. In depleted gas reservoirs, remaining natural gas may act as cushion gas. In saline aquifers, cushion gas may need to be injected before cyclic hydrogen operation begins. Dynamic simulation helps determine how much cushion gas is required, how much working gas can be delivered, and how cycling affects reservoir pressure and hydrogen recovery over time. When CCUS and underground hydrogen storage are considered together, pressure interaction becomes a central design issue. CO2 injection typically increases pressure in the storage reservoir. Hydrogen injection also increases pressure, but hydrogen storage includes both injection and withdrawal phases, creating cyclic pressure behavior. If these operations occur in the same basin or hydraulically connected formations, their pressure fields may interact. This can create both risks and opportunities. On the risk side, overlapping pressure buildup may increase stress on faults or caprock. On the opportunity side, pressure management from one operation may help support another operation if properly designed. For example, brine extraction can reduce pressure in one part of the system, creating additional storage capacity or reducing geomechanical risk. Similarly, the timing of hydrogen injection and withdrawal may be optimized to avoid excessive pressure buildup. This is why integrated dynamic simulation is important. We cannot evaluate CCUS and UHS independently if their pressure systems interact. We need a coupled framework that considers pressure, saturation, stress, and operational scheduling together. Pressure management is one of the most practical strategies for reducing risk in geological storage. When CO2 is injected into a brine-filled reservoir, the injected volume displaces brine and increases reservoir pressure. If pressure becomes too high, it can reduce injectivity, increase leakage risk, or affect fault stability. One solution is brine extraction. By producing brine from the reservoir, we create pressure relief and increase the available pore volume for injection. This can help maintain pressure below critical thresholds and improve operational flexibility. In an integrated CCUS and UHS system, brine extraction may serve several purposes. It can reduce overpressure caused by CO2 injection, help control regional pressure gradients, and support safer hydrogen storage operations. However, brine extraction must also be carefully managed because excessive withdrawal can cause compaction, subsidence, or changes in stress distribution. Therefore, pressure management is not simply about extracting as much brine as possible. It is about finding the right balance between injection, withdrawal, pressure control, deformation, and storage performance. Dynamic simulation helps identify this balance. Hydromechanical voidage management means managing the volume balance of injected and extracted fluids while also considering mechanical response. When we inject CO2 or hydrogen, we add fluid volume and increase pressure. When we extract brine, we remove fluid volume and reduce pressure. These changes affect the stress field in the reservoir and surrounding formations. The challenge is that pressure reduction is generally good for reducing overpressure risk, but excessive pressure reduction may also cause compaction or stress redistribution. This can influence subsidence, caprock deformation, and fault stability. Therefore, the best strategy is not always maximum brine extraction. The best strategy is optimized brine extraction, where pressure is reduced enough to improve safety, but not so much that deformation risk increases. A coupled hydromechanical simulation can evaluate pressure, displacement, stress, strain, and fault stability together. This allows engineers to design operations that maintain pressure within a safe range, reduce leakage risk, protect caprock integrity, and sustain long-term storage performance. In integrated CCUS and UHS, hydromechanical voidage management can become a key tool for safe subsurface energy operation. Geomechanics is essential in both CO2 storage and underground hydrogen storage because fluid pressure changes can alter the stress state of the subsurface. When pore pressure increases, effective normal stress decreases. This can make faults more likely to slip if they are already close to failure. Fault stability depends on the orientation of the fault, the in-situ stress field, friction coefficient, pore pressure, and mechanical properties of the rock. A fault that is stable under initial conditions may become less stable if injection increases pressure nearby. This is why fault stability analysis is a central part of storage risk assessment. In integrated CCUS and UHS, pressure fields may be more complex because CO2 injection, hydrogen cycling, and brine extraction may occur together. This creates dynamic stress changes over time. Some areas may experience pressure buildup, while others may experience pressure relief. By coupling reservoir simulation with geomechanical modeling, we can identify zones with increased slip tendency, Coulomb failure stress changes, or deformation risk. This information helps design safer injection rates, while locations, pressure limits, and monitoring plans. The main requirement for geological storage is containment. For CO2 storage, containment means keeping carbon dioxide underground for very long periods. For hydrogen storage, containment means keeping hydrogen inside the storage system so that it can be recovered when needed. Potential leakage pathways include faults, fractures, abandoned wells, poorly cemented wells, and weaknesses in the caprock. In many storage projects, the caprock is the most important natural barrier. It must have low permeability and sufficient mechanical strength to prevent upward migration. However, containment is not only a geological issue. It is also an operational issue. Even a good storage formation can become risky if pressure exceeds safe limits. High pressure can increase the chance of caprock damage, fault reactivation, or leakage along existing pathways. Therefore, containment assessment must combine geology, reservoir flow, pressure analysis, geomechanics, well integrity, and monitoring. Dynamic simulation allows us to test whether the storage system remains safe under different injection rates, withdrawal cycles, and pressure management strategies. This is why integrated simulation is essential for long-term confidence. Monitoring is the bridge between simulation and real-world operation. We can build excellent models, but we still need field data to confirm whether the subsurface is behaving as expected. Monitoring provides the evidence needed to validate predictions, update models, and detect potential problems early. Different monitoring technologies provide different types of information. Pressure gauges tell us how pressure evolves near wells. Seismic monitoring can help detect plume movement or microseismic activity. INSAR and GNSS can detect ground deformation at the surface. Geochemical monitoring can detect changes in fluid composition, such as pH or dissolved gas concentration. Well integrity monitoring helps ensure that wells remain safe leakage barriers. No single monitoring method is enough. A strong surveillance system combines multiple data streams. The value comes from integration, comparing pressure, saturation, deformation, seismicity, and chemical indicators together. In integrated CCUS and UHS, monitoring is even more important because operations are dynamic and may involve cyclic pressure changes. Continuous surveillance helps maintain safe operation and builds public and regulatory confidence. A simulation model should not remain unchanged after operations begin. At the start of a project, we build the model using geological data, laboratory measurements, well logs, seismic interpretation, and engineering assumptions. However, the subsurface is uncertain. Some parameters may be inaccurate or incomplete. As monitoring data becomes available, we can update the model. This process is often called history matching or data assimilation. The goal is to adjust uncertain model parameters so that simulation results better match observed field behavior. For example, if measured pressure is higher than predicted, the reservoir permeability may be lower than expected, or boundary conditions may be more closed. If plume migration is faster than predicted, high permeability channels may exist. If surface deformation is larger than expected, geomechanical properties may need revision. Model updating reduces uncertainty and improves future forecasts. This creates a feedback loop: simulate, monitor, compare, update, and optimize. In a digital twin framework, this loop can become continuous, allowing the storage system to become smarter over time. A digital twin is a dynamic digital representation of a physical system. In the context of integrated CCUS and underground hydrogen storage, the digital twin represents the subsurface reservoir, wells, surface facilities, monitoring network, and operating strategy. The digital twin connects several components. First, it includes geological and reservoir models. Second, it includes dynamic simulation of flow, pressure, saturation, and geomechanics. Third, it receives monitoring data from the field. Fourth, it provides forecasts and decision support outputs. The advantage of a digital twin is that it can help operators understand what is happening underground in near real time. Instead of only looking backward at past data, the digital twin can forecast future behavior. It can answer questions such as, what happens if we increase injection rate? What happens if hydrogen withdrawal is delayed? What happens if pressure approaches a fault zone? This makes the digital twin a powerful tool for safe and efficient operation. It transforms storage management from static planning into adaptive, data-driven control. Closed-loop optimization means that operational decisions are continuously improved using simulation and monitoring feedback. In a traditional workflow, engineers may design an injection schedule before the project begins and then operate according to that plan. However, the subsurface may not behave exactly as expected. In a closed-loop workflow, monitoring data is collected during operation. The model is updated using that data. Then, optimization algorithms search for improved operating strategies. These strategies may include changing injection rate, adjusting hydrogen withdrawal timing, modifying brine extraction rate, or changing pressure limits. The objective is to maximize performance while minimizing risk. For CCUS, this may mean maximizing stored CO2 mass while keeping pressure below safe limits. For UHS, it may mean maximizing hydrogen deliverability while maintaining gas quality and mechanical stability. Closed-loop optimization is especially valuable for integrated CCUS and UHS because the system has multiple objectives. We must balance decarbonization, energy storage, pressure control, safety, cost, and long-term reliability. Optimization helps identify strategies that humans may not easily find by intuition alone. The subsurface is always uncertain. We never know every detail of permeability, porosity, fault properties, caprock strength, relative permeability, geochemical reactions, or boundary conditions. Because of this uncertainty, relying on a single deterministic simulation can be misleading. Ensemble simulation provides a better approach. Instead of running one model, we run many models with different uncertain parameters. Each simulation represents one possible version of the subsurface. Together, the ensemble provides a range of possible outcomes. This helps us answer important questions. What is the most likely plume footprint? What is the worst-case pressure buildup? What is the probability that pressure exceeds a safety threshold? How much hydrogen can be delivered under uncertain reservoir conditions? For integrated CCUS and UHS, uncertainty analysis is essential because decisions must remain robust under different geological and operational scenarios. A good strategy should not only perform well in the average case, it should also remain safe under unfavorable conditions. This is why ensemble-based dynamic simulation is one of the strongest foundations for risk-aware subsurface energy planning. Scenario design is the process of choosing which simulation cases to run. A good scenario design helps us understand mechanisms, compare strategies, and identify trade-offs. For integrated CCUS and UHS, we can start with a base case. This case may include CO2 injection and hydrogen storage without active pressure management. Then, we can compare it with a pressure management case, where brine extraction is added. We can also simulate seasonal hydrogen cycling, where hydrogen is injected during surplus energy periods and withdrawn during high-demand periods. Additional scenarios may test different injection rates, well locations, reservoir permeability, fault properties, caprock strength, or cushion gas volume. We can also compare cases with and without geomechanical coupling. The goal is not simply to run many simulations. The goal is to design simulations that answer meaningful questions. Which operating strategy reduces pressure most effectively? Which case gives the best hydrogen deliverability? Which scenario creates the lowest fault stability risk? Good scenario design turns simulation into scientific insight and practical engineering guidance. To evaluate CO2 storage performance, we need clear indicators. The first important indicator is stored CO2 mass. This tells us how much CO2 has been successfully injected and retained in the storage formation. The second indicator is plume footprint. This shows the spatial extent of CO2 migration and helps assess whether the plume remains within the expected storage region. The third indicator is pressure buildup, which is critical for injectivity, caprock safety, and fault stability. Other important indicators include trapping efficiency, residual trapping fraction, dissolved CO2 fraction, mineralized CO2 fraction, and leakage risk indicators. For geomechanical analysis, we may also track displacement, stress change, strain, Coulomb failure stress, or fault slip tendency. These indicators help translate complex simulation outputs into practical decisions. For example, if stored CO2 mass is high but pressure risk is also high, the strategy may not be acceptable. If plume containment is good and pressure remains controlled, the strategy may be more favorable. Therefore, CCUS performance should always be evaluated using multiple indicators, not only storage capacity. For underground hydrogen storage, the key question is not only how much hydrogen can be stored, but how much can be delivered when needed. This is why UHS performance indicators are different from CCUS indicators. The first important indicator is working gas capacity. This is the amount of hydrogen that can be injected and withdrawn during storage cycles. The second is deliverability, which measures how quickly hydrogen can be produced from the reservoir. A storage site with large capacity but poor deliverability may not be useful for energy system balancing. Hydrogen purity is also important. Underground hydrogen can mix with residual gases, brine, or cushion gas. Chemical or microbial reactions may also affect gas composition in some geological settings. Therefore, gas quality must be monitored and predicted. Pressure stability is another key indicator. Repeated injection and withdrawal cycles create cyclic pressure changes, which can affect well performance, reservoir stability, and geomechanical risk. Finally, cycling efficiency tells us how effectively injected hydrogen can be recovered. Together, these indicators determine whether a UHS project is technically and economically attractive. Because integrated CCUS and UHS systems involve many outputs, it can be useful to summarize performance using an integrated storage security index. This kind of index can combine several positive and negative factors into one decision support metric. Positive factors may include CO2 trapping benefit, hydrogen deliverability, pressure control efficiency, storage capacity, and operational flexibility. Negative factors may include excessive pressure buildup, fault instability risk, leakage risk, caprock stress, deformation, and poor recovery performance. The purpose of the index is not to replace detailed analysis. Instead, it helps compare scenarios more clearly. For example, one case may store more CO2, but create higher pressure risk. Another case may store slightly less CO2, but achieve much better pressure balance and lower geomechanical risk. A security index can help identify the more robust option. This type of decision support metric is especially useful for communicating results to stakeholders, regulators, and industry partners. It transforms complex simulation outputs into a clearer ranking of operational strategies. Integrated CCUS and UHS must create both technical and economic value. From a technical perspective, the system must safely store CO2, provide reliable hydrogen storage, control pressure, maintain well integrity, and reduce geomechanical risk. From an economic perspective, the system must justify investment through carbon management value, energy storage value, infrastructure sharing, and operational flexibility. CCUS can create value by reducing emissions and supporting carbon-neutral industry. UHS can create value by storing surplus renewable energy and delivering hydrogen during periods of high demand. Integration may create additional value by sharing pipelines, monitoring systems, subsurface data, surface facilities, and digital platforms. However, the economics depend strongly on location, geology, policy, energy demand, carbon price, hydrogen market development, and infrastructure availability. Dynamic simulation can support techno-economic analysis by providing realistic estimates of capacity, injectivity, deliverability, pressure limits, and risk mitigation requirements. Therefore, integrated simulation is not only a scientific tool, it is also a decision support tool for investment, policy, and project development. Integrated CCUS and underground hydrogen storage create many exciting research opportunities. One major direction is advanced numerical simulation. We need models that can capture multi-phase flow, pressure propagation, geomechanics, geochemistry, thermal effects, and cyclic operation. Another direction is artificial intelligence and machine learning. Full physics simulation can be computationally expensive, especially when running many uncertainty scenarios. Machine learning models, surrogate models, and physics-informed neural networks can accelerate prediction of plume migration, pressure buildup, fault risk, and hydrogen deliverability. Monitoring interpretation is another important research area. We need better ways to integrate seismic, pressure, geochemical, and surface deformation data into a unified interpretation framework. Digital twins can connect these data streams with simulation models. Finally, optimization and decision support methods are essential. Future systems must not only simulate what happens, but also recommend what operators should do. This is why integrated CCUS and UHS is such a rich research topic. It connects reservoir engineering, geomechanics, geophysics, machine learning, energy systems, and climate technology. Let us summarize the 5 key takeaways from this lecture. First, CCUS and underground hydrogen storage address 2 major challenges: carbon reduction and long-duration energy storage. CCUS helps reduce emissions, while UHS helps balance renewable energy supply and demand. Second, both technologies depend on the subsurface, so they share many technical requirements: geological characterization, reservoir simulation, well design, pressure management, monitoring, and risk assessment. Third, pressure is one of the most important variables. CO2 injection, hydrogen cycling, and brine extraction all modify pressure conditions, and these pressure changes can influence storage performance and geomechanical risk. Fourth, monitoring and digital twins are essential. They allow us to observe the system, update models, forecast future behavior, and optimize decisions. Fifth, dynamic simulation is the foundation for safe and intelligent deployment. Without simulation, we cannot properly evaluate plume migration, hydrogen deliverability, pressure buildup, trapping, fault stability, or uncertainty. The overall message is clear: integrated CCUS and UHS can become a powerful platform for future low-carbon energy infrastructure. To conclude, the future clean energy system will require multiple technologies working together. Renewable energy will provide clean electricity. CCUS will reduce emissions from industries that are difficult to decarbonize. Hydrogen will support energy storage, industrial decarbonization, and flexible energy supply. The subsurface can connect these technologies by providing large-scale storage capacity. However, using the subsurface safely requires careful planning. We must understand fluid flow, pressure propagation, geomechanical response, trapping mechanisms, leakage pathways, monitoring signals, and operational uncertainty. This is why dynamic simulation, monitoring, and digital twins are so important. Integrated CCUS and underground hydrogen storage is not only a technical concept. It is a vision for smarter subsurface energy management. By combining carbon storage, hydrogen storage, pressure control, risk mitigation, and real-time optimization, we can build more reliable and sustainable energy infrastructure. Thank you very much for watching this lecture. If you are interested in CCUS, underground hydrogen storage, reservoir simulation, geomechanics, machine learning, and digital twins, please like, comment, and subscribe for more videos.